The simulation demonstrates the foundational geometric symmetry of special relativity by visualizing how a Lorentz boost simultaneously warps spacetime coordinates and energy-momentum coordinates into identical, structural mirror images. Because both systems are governed by the same linear transformation equations under the Minkowski metric, energy behaves mathematically like a temporal dimension while momentum acts like a spatial coordinate. Consequently, as relative boost velocity increases, both coordinate lattices undergo identical, diamond-like, shearing and grid tilts, where the moving reference frames close in symmetrically toward the shared, invariant 45-degree diagonal representing the absolute speed of light. This dual-panel layout highlights the core principle of physical invariance across varying frames of reference. While observed quantities like time intervals, physical lengths, individual energies, and momenta distort dramatically during relative acceleration, their combined quadratic differences remain entirely unchanged. The simulation visually proves this conservation law via dynamic lattice nodes that glide precisely along static hyperbolic boundaries, demonstrating that fundamental physical invariants, such as the proper spacetime interval and a particle's rest mass, remain strictly absolute.